Okay, this is the explanation of the competition graphs done live on the PowerPoint. So beginning with the equation up here on the upper left, we're looking at the logistic growth equation as we have described it early in the quarter. Change in population size, dn, relative to the change in time, dt, is equal to intrinsic growth rate of the population, r, times the population size, n, and then it's factored by a carrying capacity component, k minus n over k. So when n is close to k minus n becomes 0. And what we said is that we could actually think about this as being a two-species problem, so that we have then to designate each population by a number of the population, and that that the individuals of a second population may have an influence on that population growth, and we will designate that as N2, the second species, and its population. And I'll see if I can take these spaces out of there. But that the effect of that second species might not be the same as the effect of species 1 on itself. And so we're going to scale that impact by a constant. We'll just call it A, and I'll put two subscripts under here, 1 and 2, but we're not going to, oops, that didn't subscript, not going to worry about that designation very much. Just simply that the second species now can have an impact on that carrying capacity of the population. So what are we going to look for? We're going to look for something where that joint abundance of N1 and N2 results in no growth. And that means that we're looking for the place where this equals 0. So we want to look at that for that where that equals 0. And quite simply, we know that where this equals 0 when there are none of any of species 2 in the population is just the carrying capacity, K1. But you can convince yourself that if you took this out of the equation and asked what would be the population of N2 where the population size was at its effective carrying capacity, that it would be this value here, k over 1, 2. And that we can connect those points. Let's see if how I did in putting these things in. Okay, I'll move this one over just a little bit till it matches up. Is what we call a zero net growth isocline, a place where populations won't grow. Now, this is really only with respect to population 1, so we're talking about growth of population 1. So that means if it's below that zero net growth isocline of joint abundance, that population 1 can grow, and if it's above that zero net growth isocline, that populations of species 1 would decrease. Okay, with those lines. Now that so that suggests what would happen to that population growth of species 1. So we can move on and think about this with respect to species 2. The problem resolves the same way. We get a zero net growth isocline. This time the carrying capacity of N2, when there aren't any N1s in there, is simply the carrying capacity of species 2, and that the carrying capacity can be occupied, fully occupied by species 1, given the carrying capacity of species 2 and that interaction effect. And this then only relates to populations of species 2, such that when it's below that isocline, populations may increase, and when it's above that isocline, populations would decline. Okay, so that's the behavior of these zero net growth isoclines. So the question that we have then is what happens when two species are in the environment together. So I'm going to take this out so that we're going to figure that out, and we're going to put two zero net growth isoclines in there. We'll use the dashed line for species 2 and the blue line for species species 1. And there are 4 different conditions, and we'll go through each of the 4 different conditions, and you can convince yourself that those are in fact the only 4 conditions that could exist. But we have then the 0 net growth isocline for species 1 shown in the blue line, and for 2 in the black line, and the numbers representing the intersection points for both those are exactly the same as the previous 2 graphs. So then we can put those how the population would behave with respect to those places in this graph, and we see that with respect to the species 2 in this black dashed line, that populations below that black dashed line would increase, and above that would decrease. Similarly, with respect to the blue line, if population were above the blue line, it would have a tendency to decrease, and if it were below that line, it would have a tendency to increase, and that the result of this would be a net trajectory in this direction, or a net trajectory in this direction. The interesting bit comes in when we find a point that's somewhere between those 2 lines. And since we are above the threshold of the species 2, we would find that species 2 would decline. But because we're below the threshold for species 1, the blue line, that populations of species 1 would tend to increase, which would drive populations in that direction. And you can convince yourself that wherever you are within those 2 lines, that populations would go in that direction, such that even if you were at a population that was down here, that populations of species 1 would tend to increase, and that populations of species 2 would tend to decrease, and that eventually this point would end up at carrying capacity for species 1, and species 1 wins in this case. And when species 1 wins, this is then a stable equilibrium point that, if they were to be perturbed by having an addition of species 2 into the population, that species 2 would go extinct. And that makes this point right here, the carrying capacity of species 2, an unstable equilibrium point. And what does that mean? That means that if the population is in this location consists exclusively of species 2, that in fact that would be at equilibrium. But that the moment you added any of population 1 into that scenario, that it would drive the population in that direction. This would drive a decrease in population 2, and we'd end up over here at this stable equilibrium. Okay, so that's one situation. It should come as no surprise that if you flip those 2 isoclines over, that you end up with species 2 winning, and that this is the stable equilibrium point, this is the unstable equilibrium point, and that you have exactly the same condition where populations below both isoclines would increase, resulting in a trajectory moving in this direction, and above both isoclines, populations would decline, moving in this direction, and that a population between the 2 lines would favor increases in species 2 because you're below the isocline for species 2, and declines in population size of species 1, and that your trajectory would be ultimately in, oops, didn't grab the arrow, in this direction, moving towards that stable equilibrium where just a single species competitively excludes the others. Okay, so the third condition that is of interest is what happens when you have these isoclines that intersect. Just to be for completeness and thoroughness, we will once again add these vectors suggesting that when you're above or below both of the zero net growth isoclines, that you have populations that either both increase or decrease, resulting in changes in that joint abundance. And that the interesting points that we are trying to look for are in here or in here, where you're between the two isoclines. And because we're beneath the isocline for species 1, populations in here would increase of species 1. And because you're above the zero net growth isocline for species 2 in this environment, that those populations would tend to decrease, resulting in a trajectory toward the center. And that down at B, you have just the opposite, that you're below the species 2 zero net growth isocline, and so populations of species 2 would increase, but you're above the zero net growth isocline for species 1, so that they would tend to decrease, and that you'd have a trajectory that moved in this direction. This means that this then becomes a stable equilibrium with two species coexistence, and that we have an unstable equilibrium. Here, if you just had one species in the population, and you would have another unstable equilibrium point at the other one, where you had just a single species in the population. And that if you added any individuals of either species into those unstable equilibria with one species in that, it would move towards that center stable equilibrium, this one right here. Okay, so now down to the fourth and final case. And this is where you again have crossing of those isoclines, but now they're crossed in opposite directions. And that as a consequence of having them cross in opposite directions, we're going to have a different outcome. And but only in those some places. So here we have those trajectories as we saw before. Those are just the same. And that now we're looking at what happens when we're between these isoclines, and we're in a point that looks like this. Well, quite simply, we're below the species 1 zero net growth isocline. Their populations would increase, but we're above the isocline for species 2, and that we'd have a tendency to move in this direction here. And that means that the population would drift over in this direction and make this a stable equilibrium point. And by analogy, if you were up in here, same thing, you're below the zero net growth isocline of species 2, so populations of species 2 would increase. You're above it for species 1, they would decrease, and that you would move in a direction up over there, and that those both represent stable equilibrium. And that means you have two stable equilibria in this environment, and this one right in the middle is also an equilibrium point, because it's where both species would be at their zero net growth isocline, but it's an unstable equilibrium, because if you were to add either species 1 or species 2 into this environment, that they would tend to drift off to competitive exclusion, with having either one or the other species dominating. So this has a contingent result. And that, in a nutshell, in 14 minutes and 20 seconds, is the explanation for these kinds of graphs. And so what I would ask of you in the exam, and what I will ask of you in the exam, is to be able to identify stable and unstable equilibrium points, or to ask, if given a population, a joint abundance in some sector like this, like the between these lines, would it move toward the center for a two species coexistence, or toward exclusion of one species from the other? Okay, that's it.